Rolling, we were on SPO2 and then my battery died. How much battery? I didn't even see how much we got. Where? Come on over. Nope, that way. Here we are. So we're still talking about the SPO2 pulse ox. All right, bright and ambient light. So if you're in a bright sunshine environment, we're in a sunshine state in a car accident, you're trying to read it, you may get a misreading just because there's too much light. So then you can just cup it with a Band-Aid, not a Band-Aid, I don't know, something, Coban, bandage, whatever you can do to make it dark underneath it so you can stick the pulse oximeter onto the finger. Could be poor perfusion. That's why you don't pulse ox on the same hand as the blood pressure cuff. Because once it squeezes, you're going to get a misreading. Nail polish. Carry alcohol and acetone nail polish remover if you have to remove nail polish. If a vein is pulsating, could regard it as an artery if there's a high blood pressure there. In venous pulsations occurring with right-sided heart failure. This is the right side, so everything goes from the system to the right side. If it's failing, it's not pumping blood, then it's getting stopped up here and you're getting increased pressure buildup. Abnormal hemoglobin. That is what we are really using it to figure out for the most part, abnormal hemoglobin. Two types of hemoglobin normally found. We have oxyhemoglobin and we have hemoglobin methemoglobin, METHB. So there is no carbon dioxide one. It's methemoglobin or hemoglobin. Methemoglobin is a compound formed by oxidation of the iron on the hemoglobin. Whenever it's loaded with carbon monoxide, if you put a pulse ox, on someone that is saturated with carbon monoxide, it's going to read that oxygen molecule from the carbon monoxide as if it is regular oxygen oxygenating the person's blood, when in fact it is deadly for that. So they could be reading 100% and you think they're fine, but they're actually not perfusing. And that is why you read the patient, not your instruments and your tools. So what we have for that is a CO oximeter or CXO monitor. We have this, I think the Chief trucks have this. They also have the cyanide kits as well in case you inhale too much cyanide. So it measures the absorption at several wavelengths to distinguish HbO2 from COHB, your hemoglobin oxygen, from your carbon monoxide hemoglobin, methemoglobin. Determines HBO saturation, percentage of oxygenated HB compared to the total amount of hemoglobin, including methemoglobin, HbO2, and reduced HB. Okay, so it can do multiple things actually. It's interesting. Where is I going to go with this? Yeah, so different molecules have different wavelengths, which is the first I heard of this was in astronomy class. Whenever we shoot the telescope to Jupiter or even planets that are like solar systems away, light years away, and we're like, how can you tell that that planet has water? How can you tell it has hydrogen or nitrogen? It's because we're detecting the wavelengths of the light that is coming, reflecting off those planets through spectrometer. And we're doing the same thing to determine your hemoglobin. Peak expiratory, are we on? We are on. Oh, and they stopped drilling, so I can go back to this, if this is even better. Bronchoconstriction can be evaluated at the measuring peak of forcible exhalation and peak of expiratory flow meter. Increase your peak expiratory flow suggests that the patient is responding to treatment. Decreasing peak expiratory flow suggests that the patient's condition is deteriorating. Varies based on gender, height, and age. Healthy adults have a peak expiratory flow rate of 350 to 750 milliliters. That is your peak flow rate. Based on the patient in the seated position with legs dangling, we're going to assemble the flow meter, ensure that it reads 0, and ask the patient to take a deep breath and place on the mouthpiece of his or her mouth. Exhale forcefully as possible. Make sure that there's no air leaks. Perform this test 3 times. I had to take this as a firefighter when I was first getting on. It's actually a pretty difficult test, but the trick is you blow into it and you feel like you've already given up your air, but you're actually breathing a lot more than even when you feel like there's nothing left, you just keep your mouth on it and you just stay and you keep doing that for like 10 seconds, maybe, 10 seconds afterwards. It's crazy and you get really uncomfortable. Arterial blood gas analysis provides the most comprehensive quantitative information about the respiratory system. Blood is obtained through a superficial artery. This would be one AC, right AC. Blood is analyzed for pH, PaSO2. Actually, whenever I did it at the hospital, I didn't do it through the artery. Interesting. Blood is analyzed for pH, PaCO2, PaO2, and HCO3. Concentration of bicarbonate ions. Base excess indicated of acidosis or alkalosis. And SA2. I don't know what any of these are. SaO2, is that phosphorus? PHCO3 or 2 evaluate the patient's acid-base status. PaCO2s indicate the effectiveness of ventilations. PaO2 and SaO2 are indicators of oxygenation to determine ABG values between the alveolar volume and perfusion of the alveolar capillaries. Maybe it says on this page. SaO2, pH, filament. I forgot what that word was too. The body uses oxygen as fuel to make carbon dioxide as its byproduct. As the long oxygen is delivered, carbon dioxide is produced. ETO2 monitors detect carbon dioxide in exhaled air. Important adjuncts for determining ventilation adequacy. So we have types of monitors include the colorimetric, digital, and digital waveform. Provides qualitative, does not assign a numeric value. Information regarding the presence of carbon dioxide in exhaled breath after 6 to 8 positive pressure breaths. Paper inside the detector should turn from purple to yellow during exhalation. Indications of presence of carbon dioxide, and that paper does run out eventually. This is used to confirm ET2 placement and replaced as soon as possible with quantitative device. Sensitive to temperature extremes and humidity, so it's bad here in Florida. Paper inside degrades over time, yes, I remember that. Capnometer displays numeric readings, exhaled carbon dioxide, more reliable than colorimetric CO2 detector. This is on our life packs. Capnography performs the same function, but provides graphic representation of exhaled carbon dioxide. So we have waveforms, and we have digital waveforms. Here we are at 38. If we're at 48, we have a problem. This is pretty good capnography. And our, I don't know what 12 is per minute. 12 breaths per minute, respiratory rate. That's what we want, 12 breaths per minute. Waveform capnography. Provides real-time information regarding exhaled carbon dioxide levels. Displays a graphic waveform for the portable cardiac monitor defibrillator. Many I'm running out of brain power. Many portable cardiac monitor defibrillators provide numeric readings of waveforms, digital waveform capnography. Quantitative waveform capnography has many applications in emergency medicine, including the detection of bronchospasms, hypoventilation, and hyperventilation. Bronchospasms. That's what we get now. I'm thinking of fasciculation. Whenever you are intubating and you might get laryngospasms, that's what I'm thinking of. So you wait for those to calm down after medicine sets in. It's a side effect of one of the medicines. I want to say it's etomidate. Once it dies down, you can intubate. Recommended method of monitoring initial ongoing placement of advanced airway device. Capnography can indicate the chest compression effectiveness and detect return of spontaneous circulation, also known as ROSC. We want ROSC. Possible because blood that circulates through the lungs and carbon dioxide to be exhaled and measured. Carbon dioxide concentration, exhaled gases closely approximate arterial PCO2 levels, normally within the range of 35 and 25. For some reason, every patient we get, I see like 28. We're just cool with that. So carbon dioxide concentration in exhaled gases closely approximate 35 to 45. Typically, EtCO2 is approximately 2 to 5 millimeters Hg lower than arterial. Okay, so that's why. EtCO2 monitoring is limited with cardiac arrest. In a patient with a short arrest interval, exhaled carbon dioxide may be detected despite the lack of perfusion. Patients with prolonged cardiac arrest will have minimal to no exhaled carbon dioxide. Because of severe acidosis, minimal or no carbon dioxide returns to the lungs. Normal capnographic waveform. Key features of the normal capnographic waveform include consort, baseline, rate, and rise of carbon dioxide levels. In this figure, the cannula device for the monitoring end-tidal carbon dioxide in spontaneously breathing patients and an inline end-tidal carbon dioxide device can be used for the intubated patients. So here we go. This is what you put on a conscious patient, and this is for the intubated patient. It still flows through that tube, and it will pick up end-tidal. 4 distinct phases of the normal waveform. We have phase 1, A through B. This is known as the respiratory baseline. The initial stage of exhalation right here. Exhalation. Boom. Then we inhale. B to C. And I guess you're holding the breath here, and then exhale. That's a steep exhale. B to C is the expiratory U slope. Phase 3 is CD, represents the expiratory alveolar plateau. And phase 4, D through E, is the inspiratory downstroke, where fresh gas is introduced, displacing carbon dioxide, causing the waveform to return to baseline level of carbon dioxide, approximately 0 millimeters Hg. The duration, the width of each waveform corresponds to the duration of ventilations, and the space between the waveforms corresponds with the patient's respiratory rate. Am I looking at multiple waveforms, or is this one waveform? Waveform. So here we are at peak of carbon dioxide, and then once they exhale, all the carbon dioxide goes out. So we're back to 0 here. There's a buildup over time, so B to C is the expiratory U slope. Expiratory. So they have just exhaled, and it sits for a minute. Respiratory baseline. This is kind of confusing. Represents the expiratory alveolar plateau from here to here. My assumption is you breathe, expiratory, and when it's just sitting here, this is the carbon dioxide that's going through your body, right? Like it's gone into your lungs now, and now it's just sitting there. Now at the same time, you're still going through cellular metabolicism. You're still producing CO2, which is why this line slightly increases, even though nothing's happening. You're still building up slight amount of pressure. And then you breathe out, and it goes out. But it says this is expiratory U slope, upslope, so that's why I'm confused. So AB is expiratory baseline, the initial stage of exhalation. What is the initial stage of exhalation? It's, I don't know if there's multiple stages of exhalation. Abnormal capnographic waveforms. Here we go. So we have the camel hump, we have the shark fin, we have, what's the other one? There's another one, I already forgot. Shape and capnographic waveform can provide information about abnormal breathing processes such as hypoventilation, hyperventilation, and bronchospasms, rebreathing, inadvertent extubation if you accidentally displace the endotracheal tube. Hypoventilation, condition in which the production of carbon dioxide exceeds elimination. Waveforms are tall, EtCO2 corresponds high, greater than 45 millimeters Hg. Bradyapnea, also Brady, slow breathing, prolonged alveolar plateau, phase 3, C through D, and longer than normal intervals between the waveforms. Causes hypoventilation include respiratory depression, ventilatory rate that is too slow in an intubated patient, ventilatory, too slow, respiratory depression. Hyperventilation condition where the elimination of carbon dioxide exceeds production. Waveforms are small and ECO2 is corresponding less than 35 millimeters Hg. Tachypnea produces a short alveolar plateau, phase 3, C through D, and a shorter than normal interval between waveforms. Causing hyperventilation includes anxiety, metabolic acidosis, which would occur with Kussmaul, DKA. Head injury, pulmonary embolism, okay? I feel like these are test questions. Pulmonary embolism, what's happening? Hyperventilation, what's happening? Release of carbon dioxide. We want to get it out. Shorter than normal intervals of waveforms. Use of waveform and capnography in non-intubated patients. So an excellent way to assess the severity of asthma, COPD, or any pathological process that causes pulmonary air trapping. A way to gauge the effectiveness of a treatment. Use of waveform. So we're trying to figure out if they have asthma, COPD, pathological process, in any air trapping. All right, here's some examples. Let's see what we got. This looks like camel hump. This looks like shark fin, and this looks like hyperventilation. Maybe that's regular. Kind of looks like it. So what is happening with the camel humps? There is, I don't know. Shark fin as emphysema, because air is getting trapped. These figures show capnographic waveform caused by hypoventilation. Okay, so hypoventilation is A. I thought that would be it. Is that a place? Let's look at a place. Hypoventilation is A. Hyperventilation. Okay, yeah. So this is breathing slow, which is why there's only two. And then this is breathing fast. So you're breathing just like that. And then C, shark fin capnographic, that indicates incomplete alveolar emptying and bronchospasms. Bronchospasms and incomplete alveolar emptying. And it doesn't even say what D is. If inadvertent extubation occurs, you would see a flat line. Complete loss of capnographic waveform, ETO2 reading. On occasion, sampling tubing from the inline adapter to the cardiac monitor defibrillator gets obstructed with blood or other debris, blocking the flow of gas and the sensor zeroing out the waveform and ETCO2 reading. Replace the inline adapter to restore the waveform to the ETCO2 reading. Spontaneous breathing, hypoventilation, apneic, so not breathing with a pulse. Positive pressure ventilation is too slow. Apneic and pulseless. Positive pressure ventilation is too slow and could indicate ROSC. Apneic and pulseless. So your ETCO2 is going to go up with hypo and down with hyperventilation if they're spontaneously breathing. Apneic pressure is ventilation is too slow. I'm starting to lose it a little bit. Positive pressure is fast. Let's see what we got down here. CTO2, carbon dioxide. Yes, we know that. Occurs typically 40 millimeters Hg with ROSC and abrupt sustained increase. Are we done with capno? Let's stop there.